You've probably noticed that different types of injuries heal differently. Cut your finger, and given enough time, it'll heal completely, often with barely a scar. But UV damage to skin is different, and understanding why certain types of damage are harder to repair tells us a lot about long-term cancer risk. The key issue is that UV radiation doesn't just damage one thing. It's not like a cut that damages tissue structure, but leaves the cellular machinery intact. UV radiation simultaneously damages multiple systems that cells need to function properly. It damages DNA, which is your cell's instruction manual. It damages RNA, which is how cells read and implement those instructions. It damages proteins, which are the workers that carry out cellular functions. And it disrupts the membranes that keep cells organized and separate from their environment. When multiple systems are damaged at once, repair becomes exponentially more complicated. Think about it. If the DNA is damaged, but the proteins that repair DNA are also damaged, how effective can that repair be? If the RNA that tells cells how to make new repair proteins is disrupted, the cell can't even produce enough of the right tools to fix itself. You end up with a situation where the damage and the capacity to repair that damage are both compromised simultaneously. There's also something called epigenetic changes that UV radiation can cause. Without getting too deep into the molecular biology, epigenetic changes are alterations in how genes are expressed without changing the DNA sequence itself. UV exposure can add or remove chemical tags on DNA that control which genes are turned on or off. These changes can persist long after the initial damage, meaning cells might continue to behave abnormally even after the DNA itself has been repaired. It's like the cell remembers the trauma at a different level. Research has documented what scientists call field cancerization in chronically sun-exposed skin. This is where large areas of skin show molecular abnormalities, even though they look normal. The tissue has been altered by repeated UV exposure in ways that increase cancer risk across that entire field. Individual cells might look okay under a microscope, but at the molecular level, they're functioning differently than healthy skin cells. They're not quite normal, but they're not quite cancerous either. They exist in this concerning in-between state. Now, here's what's somewhat encouraging about this. Understanding incomplete healing has led to earlier detection methods. Dermatologists can now use certain imaging techniques and molecular tests to identify areas of field cancerization before any visible tumors appear. This allows for earlier intervention, whether that's increased monitoring, topical treatments, or other preventive measures. But the real message here is about prevention. Once you have widespread molecular abnormalities in your skin from years of UV exposure, you're working uphill. You're trying to manage tissue that's already been fundamentally altered. Compare that to preventing the damage in the first place, keeping your skin's repair systems intact, avoiding the accumulation of epigenetic changes, preventing field cancerization from ever developing. It's not that recovery is impossible after UV damage, but preventing that damage is far more effective than trying to reverse it after the fact.